Hello and welcome to this Unity tutorial for a follower camera for a platformer character. We are going to program a camera that will smoothly follow our character around, and it will not move past global world boundaries that we set up for it. We will use linear interpolation to make the camera smoothly follow the character around and learn about the lerp function. And then we will learn about gizmos and how to draw these rectangle around the camera that visualizes its maximum visible boundaries. We will also learn about the implications for the camera size and aspect ratio for its visible field. The easiest camera controller, and imagine this to be in quotation marks, is to simply attach the camera to the player as a child. Now quotation marks because, well, this isn't really a controller and there is no programming, but if we put the camera as a child, of course, we will follow the player around. But doing that also reveals one of the little quirks we have to deal with here, and that is that the screen is now black because the camera is on the Z position 0. If I decrease this a little bit, we can see the world again. This is because Unity is technically in 3D. So if I check this and look at it in 3D, you can see that the world here is behind the camera. So the camera is looking at it, but if I move the camera forward and past the world will disappear because the camera can no longer see it. It's no longer within the camera's view frustum or a view box. It's an orthographic camera here, of course. So when we position the camera, we always have to make sure that it is somewhat offset negatively to the world, so it is within the camera's field of vision. Of course, we don't want to simply do that because it is a really horrible camera controller. It's super static and doesn't look very nice. So instead, we write a very simple script that we can see here. There would be a transform that is our target, which we follow around, and we will define a speed that will modify how fast we follow the target around. And instead of writing any complicated logic that moves us gradually towards the target doing vector calculations, we are going to use the lerp function. Also, if you would spell it out, linear interpolation between two vectors. Linear interpolation means that we take 2 points, start and end, and we give the start value the time or t value 0, and the end value the t value 1. And any kind of value for t in between, or the interpolation in between, has some value between 0 and 1. For example, the value 0.5 in the interpolation between start and end will land us right in the middle. The math for this is actually quite simple. All that we do is we would take our start point and add a vector that goes from the start point to the end point, multiplied by some value between 0 to 1. And then this will result in a vector that is somewhere between A and B. We could easily do these calculations ourselves, of course, but we can also just use the lerp function of the vector3 class. So we need some kind of start, which of course is going to be our position. Then we need a goal, which is going to be the target's position. And we need some kind of vector t that says how far do we interpolate between the two. Then we have the assignment to transform position to set our new position. That is the lerp between start goal by the factor t. Before we plug in some values, let's reconsider what we wrote here for a second. We have in the update function, so every frame, the functions that we move a little bit closer to transform.position. At the moment we don't move at all because t is 0. Let's put in something like 0.1 here for now. That means we move 10% of the distance currently this frame between ourselves and the target every frame. Now that means that if the distance is further, of course we move faster, and if the distance is less, then we move a lot slower. And we will gradually narrow down the distance, but we would never actually 100% reach the target. Now this works actually surprisingly well. except that we cannot have a fixed number for t here, because that would mean that we move 10% of the distance every frame, no matter how many frames we have. So we have to make sure that this is frame rate independent, and we move further if we have less FPS and less far if we have more FPS. And we do this by simply using time.delta time for t. And we multiply that by speed to move further the higher our speed is. If we try this out now and put the camera controller on the camera and the player as our target, some value for speed, we can see that it doesn't work yet. We actually move where the player is, but we can't see anything. So I can move the player and the camera will follow slowly, just like we wanted to. However, of course, since the player is on the z coordinate 0, the main camera will be at the same z coordinate. We interpolate the entire vector 3 position. So we of course land also on the z-axis, exactly where the player is. Now we can fix that quite easily by simply subtracting some value for z for the target, or we can also add a new vector that has a negative value here for z. Oh, these are floats. I have to put the f in here. And this will now make sure that the camera is moving a little bit behind the playing field so we can see the game. This works great now, so let's go ahead to the next part on the agenda. That is to make sure that our camera cannot move outside of the level too far, or rather we would cap the camera's movement at a certain point. For example here, I would say that we want to stop moving the camera if we hit this distance on the x-axis, so we don't get into a situation where we just have a whole lot of nothing to our right. Right? So the camera should stop moving at some point. The problem with this though is that it depends on the aspect ratio of our camera, what we can see to our right and left. So if I go and change the aspect ratio here, you can see now I can barely see the edge. However, if I go to 16:10, I cannot see that edge anymore. And these are the two main aspect ratios of Mac and Windows computers, but it of course gets even worse if you go for something like a smartphone resolution in a vertical screen, or the 4:3 resolution of all the monitors. We also have to consider the size of the camera, or the orthographic size, since we're currently in orthographic projection. Orthographic projection means that we have a certain portion of the world visible, defined by the height and width of the camera, or by the size and the aspect ratio. So currently the size of 5 means that from the middle of the camera to the top, it's 5 units in the world. If we increase this value, of course, we have an effect like zooming out, because more units are visible within the camera rectangle. Set this back to 5. And then the aspect ratio defines the relative width respective to the height. We will implement a set of values that define the global maximum values for x and y coordinates that the camera can have visible. This means global maximum x will be the value inside the world on the x-axis that defines the maximum visible boundary. So the camera will not move further to the right than this line when it hits it with its right border. So we have to calculate the distance based on the current orthographic size and aspect ratio of the camera to the right border of it when it hits the right maximum on the global axis. So after we lerp to the new position, we should actually check if this position would be outside the visible boundaries. So let's save this first in some new variable, and then calculate what our boundaries are. The maximum x would be our global maximum x subtracted by the camera's size multiplied by its aspect ratio. And instead of grabbing the camera component, we can also just use the main property of the camera class, which will always return us whatever camera is tagged as main camera. For the maximum Y, of course, we don't need to consider the aspect ratio, we just need to know the orthographic size, since that directly describes the height of the camera. The aspect ratio simply converts our height into the respective width. Then for the minimum values, we take the global minimum and add whatever offset we need to find the minimum position to the left that we can place the camera without overstepping our global boundary. Now to check our new position that we lerp to, whether or not it is within the maximum values, we don't have to do a whole lot of if-else statements and then reset the value to whatever minimum or maximum would be overstepped. We can simply use the clamp function. mathf.clamp will take the value that we want to check for its boundaries, and then it will take the minimum and the maximum to check against. Clamp will return the value if it is between the minimum and maximum, or the given minimum if the value is lower, or the given maximum if the value is bigger. So it's perfect for our scenario here. Then we clamp the x and y values of our new position against the calculated minimums and maximums, and finally apply our new position back to our transform. To test this out now, I have added some values here for minimum and maximum in the inspector, 10 for the maximum on each axis and -10 for the minimum. So if I hit play now, and I will go to the right, the camera will follow until I hit the maximum. And then it will simply stop. And it also works if I change my aspect ratio. So if I go now and go to a smartphone vertical resolution, I can go a lot further to the right, of course, because the camera is not so wide, but it will stop at the same global boundary. Our new problem now is to figure out which kind of values are good on which axis. And this will be very tedious to test out, okay, if I go here, 10 would be somewhere around here, so maybe 13, maybe 14, and you would have to test a lot and go back and forth. But we can easily visualize the boundaries using gizmos. So we are going to draw some lines inside the scene view that visualize the global boundaries of our camera. Gizmos are these elements that you can see here, like the camera icon or the camera rectangle or anything else that is not visible inside the game view. And luckily we can draw our own. We can do that in our script using the onDrawGizmos function or onDrawGizmos which will only be called if we have selected our object in the hierarchy. The special thing about the gizmo functions here is that they are called while we are in edit mode too. So we don't have to run the game in order to see our debugging information. It also is visible when we are not in play mode. So here I have added the draw calls to draw our custom gizmo lines. First I set the color to green, and then I use gizmo.drawLine to draw lines between two given vectors, a start and an end. And we just do that for each of the minimum and maximum values for each of the axes. Note how we have to set the color first, and then the draw calls actually don't take a color input like debug.drawLine would. So when you draw gizmos, you first have to set the color, draw your gizmos of that color, and then change the color if you want to draw more gizmos of a different color. If we have a quick look at the available functions here, you can see that you can also draw cubes, frustrums, icons, lines, meshes, rays, or whatever else. So with gizmos, you actually have a lot more functions available than simply drawing lines with debug drawline. We can try these out now. You can see if I have my camera selected, I can see the green outline that we just draw in the gizmo draw codes. Then I can change my values to something that I like, and the lines will adjust immediately. Hit play and try out if this works. So now you can see how the camera will stop following when we hit the borders. Perfect. To sum up, we learned about linear interpolation and how we can use that in the update function to gradually move towards another object with higher speeds if we are further away and slower speeds if we are close, giving us a nice smooth camera follower. Then we learned how to use the global maximum and minimum values to cap the camera movement and make sure that it doesn't follow over a certain border that we give it, and how to use gizmos to visualize those, and particularly how to respect the aspect ratio of the camera to see what kind of elements would be visible and not visible, and that any kind of final user might have any kind of different aspect ratios on the screen that they play the game. So when you position objects, like the sign that I put here to the right, be aware that some users might see it and some users might not, depending on what kind of screen they have. So any kind of object positioning and camera movement should be programmed keeping in mind that there is different screens with different aspect ratios out there.